bromine atoms go, this bromine atom goes to the carbon atom with the lesser hydrogen atom. So this is our Markovnikov rule. Now suppose I am going with the anti-Markovnikov rule. Now this anti-Markovnikov rule will only work in the case of when peroxide is given and only bromine atom is used with this in this HBr, meaning in this HX. So in that scenario the process gets reversed. What that means is this bromine atom will go to the carbon atom of the double bond with more hydrogen atom, that means with the CH2Br, and this hydrogen atom will go with the carbon atom with the carbon atom of the double bond with the lesser hydrogen atom, so it comes here CH2. This is anti-Markovnikov rule. Okay, so the fourth concept in this, or I should say the third concept in this preparation, methods of preparation of haloalkanes and haloarenes comes as halogen exchange. So in this we are going to study two name reactions, which are Finkelstein reaction and Swart reaction. Now what do you mean by Finkelstein reaction? Okay, so what do you mean by Finkelstein reaction? Finkelstein reaction is nothing but very simple reaction. So you are using Rx with NaI, NaX get removed and you get Ri. So this should be used with triacetone. Next, so here what happens is NaX gets removed, right? It is precipitated. So this facilitates forward reaction with reference to Ley-Chartley's principle. Next we are studying Schwarz reaction. This is an halogen exchange only, which is our third method of preparation. So Schwarz reaction basically means we are using no condition is used here like dry acetone. So we are using simply CH3 bromine. Okay, so any bromide or chloride can be used. Here also X is equal to chlorine or bromine. Here also you can use X, which is equal to chlorine or bromine. So you are using a simply CH3X or RX you are using with AgF. So when you use this, so your Fx, your AgX gets removed and you are getting RF. So this Schwarz is used for the production of alkyl fluoride, and Finkelstein is used for the production of alkyl iodide. Next we are moving out to the physical properties. Now physical properties is our eighth is our physical properties. So alkyl halides we are going to study the physical properties. In this we are going basically studying the melting point, boiling point, density and solubility. Melting point and boiling point. So more the surface area, more the boiling point, because the van der Waals forces will be more. If the branching gets increased, the van der Waals forces also reduce, surface area also gets reduced, hence the boiling point and consequently the melting point will be lower. Okay, so now for the same alkyl group, the boiling points of alkyl halide decrease in the order iodo, bromo, chloro and fluoro. Okay, now why this happens? This is because when the mass and the size of this atom is getting increased, consequently the van der Waals forces also increase and the boiling point also increase. Whenever the van der Waals force increase, the boiling point increase. Okay, so now the boiling point of the isomeric dihalobenzenes are similar, but when compared to the ortho and the para dihalobenzene, what you will notice is the para one are having higher boiling point. For example, if I am taking para dibromobenzene, this will have higher melting point and boiling point when compared to ortho dibromobenzene. Now why? Now this is because the para one, this one gets fits in the crystal lattice better than the ortho one. So that's why its melting point and consequently the para point, sorry, melting point and the boiling point is more because of its symmetry when compared to the ortho and meta isomers. Now for the density, so the bromo, iodo and chloro derivatives of the hydrocarbons are heavier when compared to the normal hydrocarbon, meaning basically haloalkane are having more density when compared to the normal hydrocarbon. This is because when you are using a halogen, its atomic mass is more. Density is nothing but mass by volume. Since the mass is increased, the density also increases. Alright, so if you notice, the density increase in this order, same order as we are studying for the melting point and boiling point. Next is the solubility. So for the solubility part, what we observe is haloalkanes are very slightly soluble when you consider in water. They are soluble in organic solvents, but they are not soluble in water. Why? So whenever suppose we are dissolving this haloalkane particle in water, so what should happen is the bond between the haloalkane compound should break and new bond should be formed between the haloalkane and water particles. So when the haloal the we will mix the haloalkane and the water, so the new interactions, the energy released when the haloalkane and water molecules interact and form new bonds is very less to break the previous bonds between the haloalkane molecules. So consequently, the haloalkane molecules are not able to dissolve in the water. Now next we are going to study the nucleophilic chemical reactions of the haloalkanes. So in this we are going to study our first one, nucleophilic substitution reaction. So these are chemical reactions of haloalkane. So in this we are going to study nucleophilic substitution reaction. So in this a table 10.4 is given in your textbook. So what happens is basically you are having a haloalkane and you have a nucleophile. So you will get RNU and this halogen gets removed. Okay, so now we'll be seeing the table. For the table, you will get reagent, nucleophile and the substitution product and class of main product. For example, if you observe, so when this R haloalkane reacts with KCN, what will be produced? RCN, that is our alkyl cyanide will be produced, but with AgCN, cyanoalkane will be produced. Isocyanide will be produced, and with AgNO2 will produce alkyl nitrite, that is RO and double bond O, and with KNO2 will be produced nitroalkane, which is RNO2. Now the main question is why with KCN we are getting alkyl cyanide and why with AgCN we are getting alkyl isocyanide. So this is because when you consider KCN, this is a ionic compound. Okay, and when you consider AgCN, this is a covalent compound. So because this is a covalent compound, so what happens is since nitrogen is having a free electron pair to donate, it is freely forming an alkyl isocyanide. But in the case of KCN, why we are getting alkyl cyanide is since this is a CC bond is more stable than a NC bond. In the case of the reaction with KCN, we are getting alkyl cyanide. Now in the case of AgNO2 and KNO2, here we are getting alkyl nitrate and here we are getting with KNO2 nitroalkane. This is because again this KNO2 is an ionic compound, right? So, and this AgNO2 is a covalent compound. So what happens is the case of AgNO2, it is a covalent compound, and so what happens is oxygen acts as a nucleophile and we get alkyl nitrate. But in the case of KNO2, this is an ionic compound. So nitrogen acts as the nucleophile and we are getting nitroalkane. So next we are going to study what are ambidient nucleophile. So ambidient nucleophile basically are the nucleophile like cyanides or the nucleophile like nitrate. Nitrate are ON double bond O. So here the nucleophile can be oxygen or nitrogen, and similarly here in the case of cyanide, the nucleophile can be carbon or nitrogen. As you can observe, sometime we are getting oxygen, sometime we are getting nitrogen in the case of this nitrite, and in the case of cyanide, sometime we are getting carbon, sometime we are getting nitrogen as the nucleophile. So next what we are going to study is SN2. So this mechanism of these nucleophilic substitution reaction can be understood by SN1 and SN2 reaction. Now SN1 reaction, I'll be teaching this in short, SN1 and SN2. So in the case of SN1, the alkyl halide should be tertiary, secondary, primary, priority order, and SN2 primary, secondary, tertiary. Now the one more thing, so listen carefully. Now here the concentration in the case of SN1 depends, the rate depends only on the concentration of the, see what is a nucleophilic substitution reaction. You are having a haloalkane, you are having a nucleophile, and you will get a RNU compound, and correspondingly X minus would go away. So here the rate depends on only on the nucleophile, sorry, in the case of SN1 only on the haloalkane, whereas in the case of SN2 the rate would depend on both the reactants Rx as well as the nucleophile. Alright, so next our step of differences. SN1 is a two-step mechanism. What do you mean by two-step mechanism? In the first step, our nucleophile would be removed and you'll be getting a carbocation, which is in the shape of a trigonal planar carbocation. And in the second step, our nucleophile will get attached. This is a two-step mechanism. Now in the case of SN2 reaction, this is a one-step mechanism. Okay, meaning at the like this is a one-step mechanism. So next, our point of differences, in this it is retention of configuration, whereas here in the case of SN2, inversion of configuration takes place. This point of difference is very important. SN1 require polar protic solvent, alright, whereas SN2 reaction involve polar aprotic solvent. Polar aprotic solvent like acetone, polar protic like water. Now why? Because when I consider polar protic solvent in the case of SN1, what happens is it helps to lower the energy of the transition state, which leads to the formation of the carbocation, and hence our rate determining step, which is the first step, which is the formation of the carbocation, that it helps to increase the speed. Whereas when I consider the polar aprotic solvent, these only interact with the cation and hence they leave the anion alone. This helps to increase the nucleophilicity of the anion. That's why these polar aprotic solvents helps in the SN2 reaction. Whenever you are considering either SN1 or SN2 reaction, in both the reactions, what will happen is, for the same given alkyl group, the reactivity of the halide will follow this order: iodo, bromo, chloro, and fluoro. Okay. Now one more thing. In the case of SN1 reaction, alright, whenever you come across a allylic or a benzylic halide, right, they will show higher reactivity towards the SN1 reaction. Why? Because the carbocation formed in the first step is resonance stabilized. Okay, so that's why allylic and benzylic halide will show high reactivity towards SN1 reaction. So next we are going to study some stereochemical aspects of nucleophilic substitution reaction. What are we going to study? Stereochemical aspects. Now what are those stereochemical aspects? Let us see. So those are optical activity, chirality, retention, inversion and racemization. So let us see. First of all, what do you mean by optical activity? Optical activity means when the light can be rotated, that means optical activity. So that is not important, but important is chiral or achiral carbon. For example, if you are having a carbon group that is attached to 4 different groups, suppose R dash, R double dash and R triple dash, this is basically known as a chiral carbon atom or a asymmetric carbon atom. So if suppose this carbon atom was attached to same atoms, then this carbon atom is known as a chiral carbon atom or symmetric carbon atom. So such carbon atom which are achiral will not show optical activity. Okay, they will not rotate the light, and whereas these carbon atom which are chiral in nature, which are asymmetric in nature, they will show optical activity. These one. All right. So after these, what we are now, these are this carbon atoms also known as stereocenter. All right. By retention was as in the case of SN1 reaction, and inversion as in the case of SN2 reaction. So both these would require the do not require a chiral carbon atom, meaning the having a chiral carbon atom is only required for the stereochemical aspects of the reaction. For the SN1 or SN2 reaction to occur, the presence of a chiral carbon atom is not required. Meaning, if in a SN1 reaction a chiral carbon atom is present, then you will get a racemic mixture, and in the case of SN2 reaction, if a chiral carbon atom is present, you will get a inversion configuration. Now, what do you mean by racemic mixture? Now, before racemic mixture, let us know what do you mean by the term enantiomers. Enantiomers are basically optical isomers which uh, which are or as stereoisomers which are related to each other as non-superimposable mirror images, that are enantiomers. Now, what are stereoisomers? Stereoisomers are basically those isomers Stereoisomers are basically optical isomers which can rotate in the right, which means plus, or in the left, meaning the minus directions. Now, when the plus is known as dextrorotatory and the minus is known as the levorotatory. Now, when you are having two enantiomers in the same proportion in a mixture, so then what will happen is that the optical rotation of one compound will be cancelled by the other, and the net mixture will have no optical rotation. So that mixture is known as a racemic mixture. Alright. So after this we are going to study next about our elimination reactions. Under the chemical reactions of haloalkanes. So in our elimination reaction, first of all, we are going to study beta elimination reaction. What do you mean beta elimination? So this is a carbon CH2 and halogen. So and here you are having CH3 group. Okay, all right. So this carbon atom to which the halogen attaches alpha, and the next carbon atom to which is known as beta. All right. So what will happen here is what is going to happen is we are in this halogenation, we are going to study dehydrohalogenation reaction. So the preferred product is that alkene which has the greater number of alkyl groups attached to doubly bonded carbon atoms. Alright, so we are studying dehydrohalogenation. This is also known as Set-Zipf rule. Set-Zipf rule. Alright, so what is going to happen here is when I am using a base, suppose OH minus, alright, and I am performing this reaction, so what is going to be removed is my halogen. Alright, my halogen is going to be removed. See, observe here. I am having here, always remember that the beta hydrogen will be removed along with the halogen. Alright, so I am having here CH2 with my halogen, and here I am having carbon, one hydrogen I'll show like there, and one more H2. So my base is coming. Alright, my base is coming. So what will happen, my halogen gets removed as X minus, and this bond comes here as a double bond, and this base takes this hydrogen away as water, plus I am getting a alkene. So this is my dehydrohalogenation reaction. Now when to follow Set-Zipf rule? For example, I am taking 2-bromopentane, right? What do you mean by 2-bromopentane? We are having a pentane, CH3, CH, CH2, CH2 and CH3. Now here you are having bromo. Now when you are reacting with this base, OH minus, and here also OH minus, so this is beta and this is also beta. Okay, so two beta hydrogens can be removed. Alright, so which one you would remove? Suppose I have removed from the first one. This one I am removing. CH3, CH, bromine gets removed. Now this hydrogen gets removed, and that one bond of this hydrogen atom, see, this one bond of the hydrogen atom come here, and this hydrogen gets removed. So CH, double bond, CH, CH2, CH3. Now if suppose other way around it would have happened, meaning this beta hydrogen would have been removed, then in that case the product would have been CH2 double bond CH, CH2 double bond CH, and then again CH2, CH2 and CH3. Alright, so in that case the product would have been like this. So what Set-Zipf rule says, to both these double bonded carbon atoms, the one which has greater alkyl groups attached to the doubly bonded carbon atom, that has more stability, that product is more preferred. So out of these, which product would be more preferred? Out of these, which more product will be preferred? So that product is going to be pentamine. Why? Since this carbon atom has one alkyl group attached to it, meaning this one, and this carbon atom has how many? This also has one alkyl group attached to it, whereas if you observe here, this carbon atom has 0 groups attached to it, alkyl groups, and this has one. So instead of these alkyl group, what you can take is the one which is having lesser hydrogen atoms, the one compound of the, when you see the doubly bonded carbon atoms. So the one which has less, when you add up both these hydrogen atoms, here is 2, here is 1. So what you get? 3. Similarly, here is 1 and here is 2, but you get 2. Here is 1 and here is also 1. You get 2 hydrogen atoms which are attached to the doubly bonded carbon atoms. So which number is less? This 2 is less than 3. So this compound will be more preferred. Okay. Important topic which is in a box is elimination versus substitution. Which your method you should prefer. So in this scenario, whenever you are having a bulkier nucleophile, will prefer to act as a base. So when you are having a bulkier nucleophile, that would act like a base, and that would abstract a proton rather than approach a tetravalent carbon atom due to steric reasons. So therefore, a bulkier base would abstract a proton, meaning it would go for uh, a elimination reaction. Why? Due to steric reasons, it does not needs to perform. It does not needs to perform a substitution reaction. And if I am having a opposite of bulkier is a small nucleophile, in that scenario I will go for substitution. So now if I go for my like primary, secondary and tertiary, so my primary alkyl halide would prefer SN2, a secondary alkyl halide would prefer SN2 or or it can also prefer elimination. It depends on the strength of the nucleophile or else on the carbocation formed. Not the carbocation but on the strength of the nucleophile. Now similarly, if I am going for a tertiary halide can go for SN1 or it can go for elimination. Now that depends on the strength of the intermediate carbocation formed or of the nucleophile. Okay, so now the third part in this chemical reaction of haloalkanes comes the reaction with metals. In this reaction with metals, we are going to study one important reaction, which is two important reactions, which are Booth's reaction and reaction with Grignard reagent. Grignard reagent and with organometallic compound like RMgX. In this compound, this is here is del minus, here is del plus, and here is del minus. So this is also polar bond. This is also polar bond. Alright, so we are having two polar bonds. So what we are going to study, we are having Rx and I am having an Mg, and we are going in dry ether. So I will be having RMgX. This is my Grignard reagent. This is an organometallic compound. So now, how do you? Grignard reagents are highly reactive, and they will react with an proton to give hydrocarbon. So that's what dry ether is being used. Understanding. So that this Grignard reagent does not get converted to our corresponding hydrocarbon. So otherwise what would have happened is, if this dry ether won't be present, this Grignard reagent would go with water and it would be converted into RH and MgOHX. Next is Booth's reaction. What do you have in Booth's reaction? Booth's reaction is basically, I am having Rx and I am Rx, and in between I am having 2Na. Alright. This also needs to be in dry ether. So this 2Na and this X goes as 2NaX, and I am getting RR. Okay, this reaction is used to double the chain of carbon atoms. Next is the reaction of haloarenes. In this we are going to study nucleophilic substitution reaction and electrophilic substitution reaction, and then reaction with metals. First of all, the nucleophilic substitution reaction. Now these phenols are haloarenes are very less reactive towards nucleophilic substitution reaction. Why? Due to resonance effect. Okay, first reason is resonance effect. Why? Because they obtain a partial double bond character. See, this bond acquires a partial double bond character, then a nucleophile finds it difficult to get substituted. Next is difference in hybridization of carbon atom in CX bond. In haloarene, this carbon atoms is sp2, so S character is more, so this is more electronegative. That's why nucleophile substitution reaction is difficult. Whereas in the case of haloalkane, that carbon atom will be sp3, S character is less and electronegative character is also less. Hence, what will happen? Nucleophilic substitution reaction can happen more easily. Next is instability of the phenyl cation. In case of haloarene, the phenyl cation which is formed as a result of self-ionization will not be stabilized by resonance. Hence SN1 mechanism is ruled out. Okay. So because of what do you mean phenyl cation? What do you mean phenyl cation? This is phenyl cation. Okay. Now what do you have? Because of the next is the last reason. Because of the possible repulsion, right? It is less likely for the electron rich nucleophile to approach electron rich arene. Next is replacement by hydroxyl group. Now NO2, we are going to study interesting character about nitro group. NO2 group is electron withdrawing group minus a effect group. So what happens here is when I am taking chlorine, alright, and I am having NOH at 623 Kelvin and 300 atm, and I am having H plus. This would give me phenol. But consequently, if I reduce the temperature to NOH and 443 Kelvin, with this I am then giving H plus, then also I will be getting a phenol. But instead of this chlorine, instead of this haloarene, I am having my NO2 attached at the para position. Alright. Now, if I am having NO2 attached at para, ortho and para position, I just require NaOH and 368 Kelvin, and after this I require H plus to get my OH phenol. But NO2 and NO2 will remain here also. Now I just made a mistake here, just a second. As you can see here, OH and here also should come NO2 should have been there at para position. Alright. Okay. So after this, as you can see, as my NO2 group have increased, my temperature has decreased. So my last would be, I am taking my chlorine, haloarene and this NO2 at ortho, para and again at ortho position. So what I am doing here, I am just taking warm, I am just simply heating the solution with water. So what I'll get, I'll be getting my simply phenol, and with this I'm getting a NO2 and NO2 here also. These should be alright. So what has happened is, whenever you have to notice, I am using NO2 group to decrease the temperature conditions only at ortho and para positions. Why not at meta position? Because if you observe the resonance structure of this haloarene, chlorine, we will observe the negative charge to be present only on the ortho and para position, not on the meta position. Now since NO2 is an electron withdrawing group, it needs to withdraw only the electron where they are present, and those electrons are present at only in the ortho and para position. So that's why NO2 is being used only at ortho and para position. Now one more thing, as you can see this OH on the top and NO2 at two ortho position and one at para position. This compound is also known as picric acid. So next we are moving towards the electrophilic substitution reaction of haloarenes. So though there are haloarenes are deactivating, the halogen is deactivating, but they are ortho and para direct. So for example, we are going to study halogenation, nitration and sulfonation. And what do you mean by halogenation? That is nothing but Friedel-Crafts reaction. We'll be taking our chlorobenzene Cl2 in anhydrous FeCl3. Now with this I will be getting parachlorobenzene and orthochlorobenzene. Now why is the para product major? Because they are more stable, they have more symmetry, due to which they are more stable products. That's why they are major. Para products are major. Now after this, as you can see in the para products, these two halogen atoms are far away from each other. Hence they are more stable rather than the ortho product. Now next is nitration. So in the nitration, what we are going to see, a nitrating mixture should be there, which is our concentrated HNO3 or is HNO3 and concentrated H2SO4. So that will react with my chlorobenzene HNO3 and concentrated H2SO4, and what I will get is ortho nitrochlorobenzene just a second, ortho nitrochlorobenzene and para nitrochlorobenzene. These two products I will be getting. Again, para is major and ortho is minor. After this I am going for my third reaction. My third reaction is sulfonation. Sulfonation is nothing but I am taking my chlorobenzene. With this I am taking concentrated H2SO4 and I am going to heat. So I will be getting here SO3H and here also SO3H. Alright. So this is known as, see, this is 1, 2, 3 and 4. Alright. This is known as 4-chlorobenzene sulfonic acid, and this is 1 and 2-chlorobenzene sulfonic acid. Again this is major and this one is minor. Okay. Now after this we are going to study Friedel-Crafts reaction in the electrophilic substitution reactions. Now what is Friedel-Crafts reaction? I am taking my haloarene chlorobenzene and reacting it with CS3Cl in anhydrous AlCl3 or else FeCl3. So what am I getting? I am getting 2-chlorotoluene and 4-chlorotoluene. This is major. Alright. Second, I am taking again this my haloarene, but with this I am taking anhydrous FeCl3 or else AlCl3, and I am using CS3COCl. So I am going to get, now before this I wanted to know what is acetophenone. Acetophenone is nothing but CuCS3 with benzene ring. This compound is acetophenone. So here I am getting, when I am treating haloarene with anhydrous FeCl3 and CS3COCl, I am getting 2-chloroacetophenone, which is minor, and 4-chloroacetophenone, which is major. Okay. So after this we are going to study our Third reaction of chemical reaction of haloarenes, which is reaction with metals. First of all, we are going to study Woods fitting reaction. I have taken my haloarene, and with this I am taking sodium. I'll take 2 sodium and I'll take C. What I'm doing, I have taken a haloarene, I have taken a haloalkane. So my haloalkane and haloarene will be reacting together in this reaction with 2 sodium. Alright, so then again this with Woods reaction, Woods fitting reaction, so dry ether would be used as the reaction condition. So what is going to happen is this X and this 2Na and this X will be removed as 2NX, and I'll be getting this as my product. Alright, so then what is this known as? This is known as alkylarene. Alright, so next is my fitting reaction. This was Woods fitting reaction. Now I am going to study fitting reaction. What is fitting reaction? So aryl halide will give me analogous compound. What are analogous compound? See, I am having 2 haloarene and I am having 2 sodium. This I am taking in dry ether. This is fitting reaction. Okay, so my this 2Na and this X would be removed, and I will be getting these 2 benzene rings joined. So this is known as diphenyl, and this reaction is fitting. This reaction is Woods fitting. Okay, next I am moving to the last part of this chapter is polyhalogen compounds. But a polyhalogen compound with carbon compounds containing more than one halogen atom are known as polyhalogen compound. First of all, we will be studying about dichloromethane. Dichloromethane is also known as methylene chloride. So this is basically used as a solvent, as a paint remover, propellant in aerosol, and as a process solvent in manufacture of drugs. It is also used in metal cleaning and finishing solvent, and exposure can lead to dizziness, nausea, tingling and numbness in the fingers and toes, and with the contact of eye can burn the cornea. Next is trichloromethane or chloroform, that is CHCl3, trichloromethane or chloroform. So this is known as solvent. This is used as solvent for fats, alkaloids, iodides and other substances. Major use is in the production of freon refrigerant R22, chloroform, and general anesthetic in surgery, but being replaced by less toxic, safer anesthetics such as ether. And inhaling will depress the central nervous system. And when this chloroform is exposed to the air, to the atmosphere, it is oxidized by the air in the presence of light also, and you will be getting phosgene, which is nothing but phosgene, which is COCl2, and as side product you will get HCl. Now one more fact, whenever this chronic chloroform exposure will damage the liver, their chloroform is oxidized to phosgene, which is COCl2. Okay, now what is phosgene? Phosgene is also known as carbonyl chloride. So next is triiodomethane or iodoform, which I can write it as CHI3. That is known as that is used as an antiseptic, but that is used as an antiseptic when we are getting free iodine, after the liberation of free iodine. So next is tetrachloromethane or carbon tetrachloride, that is number CCl4. That is used in manufacture of refrigerants and propellant for aerosol cans. Also used as feedstock in the synthesis of chlorofluorocarbon. So it was widely used before as a cleaning fluid and a degreasing agent, but now it causes liver cancer and also head lightheadedness, nausea, and vomiting. And it can also cause permanent damage to nerve cells. Exposure to carbon tetrachloride can make the heart beat irregularly or stop. Chemical can irritate the eyes on contact. It can, when released in the atmosphere, carbon tetrachloride, it can deplete the ozone layer, and it can lead to the human exposure to the ultraviolet rays, which can lead to skin cancer, eye diseases and disorders, and disruption of the immune system. Next is freon. So the chlorofluorocarbon compounds of methane and ethane are collectively known as freon. They are stable, unreactive, non-toxic, non-corrosive and easy liquefiable gases. Freon 12, which is CCl2F2, as you can see, this chlorofluorocarbon of compounds of methane and ethane, is one of the most common freon. It is manufactured from tetrachloromethane, which is carbon tetrachloride, by Schwartz reaction. I studied before, this was Schwartz reaction when our haloalkane with HEF produced alkyl fluoride. So freon 12 CCl2F2 is produced from carbon tetrachloride using Schwartz reaction. So now they are produced for aerosol propellant, refrigeration and air conditioning purposes. So most freon that is used in the refrigeration eventually makes way into the atmosphere, where it diffuses unchanged into the stratosphere. In stratosphere, freon is able to initiate radical chain reactions that can upset the natural ozone balance. Next is DDT. So DDT was used as the first chlorinated organic insecticides, but what happened was DDT was being used so much for the against malaria and lice which carry typhus, but what had happened, they had developed resistance to DDT, and also they had high toxicity towards fish. The chemical stability and its fat solubility had the problem. DDT is not metabolized very rapidly by animals, instead it is deposited and stored in the fatty tissues. And what happens is, if it ingestion continues at a steady rate, DDT builds up within the animal over time. So we'll see the structure and the chemical name, IUPAC name of DDT. This is the IUPAC name of DDT, which is, see, this is ethane 1 and 2. So 2,2 bis, meaning 2 are there. Now in the bracket 4 chlorophenyl, and by bis because 2 are there. And what is the parent compound? Parent compound is 1,1,1 trichloroethane. Alright, this is in an alphabetical order. Our bis is not taken for the alphabetical order. Alright, so this is how the naming goes. And its common name will be pp-dichloro-diphenyl trichloroethane. So these notes you can find in the description section. You can find it as a link, and if you have any doubts you can post it in the comment section. Thank you for watching. All the best.